Let's start our lecture today. We will continue with bot plot. Yesterday, I have introduced you to the basis for bot plot, and we plotted in two examples. But today, as I mentioned yesterday, we will not be able to draw the exact bot plot. We will do what we call straight line approximation. We will do straight line approximation. In order to do straight line approximation, we have to know a few for certain there are many cases, many form of transfer function, and each form have their own bot plot. So we have to know that. Before that, I would like to inform you that you will not be asked to sketch the root locus in the exam. There will be no question on sketching root locus. I just want to give you some knowledge on this, but the theory you should know. That's why I also make effort to also teach this one. Although this will not be asked, you should know because that is the theory, and also in the exam you will be given the bot plot. Similar to root locus, we do not ask you to draw root locus or to sketch root locus. We will give the root locus in the exam. Similarly, we will give the bot plot in the exam. So you have to read the bot plot, have to understand what that means, and also maybe sometimes they need question ask you to modify the bot plot. That's why here also important to know how it is drawn, how it is sketched. Hopefully that will improve your understanding on bot plot. Okay, first we look into if we have GS equal to just a constant K. GS equal to K, J omega. Again, we normally change to J omega. Also K because not S here. The magnitude in dB is 20 log K. It's a constant 20 log K. It depends on the value of K and the angle or the phase angle. K, we know K is here. K, so the value angle is 0. It's on the real axis to the on the left, on the right, so 0. If we plot root locus, this is for magnitude in dB, omega in radian per second, also omega here, radian per second. This is for phase. Okay. 20 log K is just a constant. 20 log K depend on K. 20 log K dB. Okay. Sorry. Phase is 0. So it should be 0 here. 0 degree is on this line. Okay, so that is the first one. So you know when K is like this. Let's move to this one, S. This is the other form. So now we have S. GS equal to, I substitute J omega equal to J omega. In order to get the the magnitude in dB. Sorry, the magnitude first, not in dB. We start with the one normal one. Magnitude is j omega. J omega is here. J omega. J omega. So we know the magnitude is omega. The magnitude here, omega. In dB, if I want in dB, (20 log omega). Okay. And the phase angle 90 degrees because it is on the imaginary axis, positive imaginary axis. So 90 degrees. That is S. And how we can draw, we can sketch on the root log on the board plot. So if we have this omega in radian per second, this is magnitude in dB. Okay, let's see if omega equal to 1, log 1 is 0. Okay, you will see log 1 equal to 0 when omega equal to 1. So it's 0 dB here. When omega equal to 0.1, 0.1 you get omega negative 1, 10 to power of minus 1. So it will be minus 20. It will be here. When omega equal to 10, it will be log 10 is 1, 10 to power 1 will be 20 dB. Is here. Okay, so it's actually if you continue 100 will be 40. 10 to power log 100 is 2, so 40 dB. So it will be like this. It will be a straight line. Okay, something like this. It will be straight line. It's also shown here. You can see here the same. And past 0 dB at 1 radian per second. That is Gs equal to S. When when Gs equal to S, we will get this. And you can see here, if this is the slope. This is 20. This is one decade. We call 1 decade. So we call this a line with slope 20 dB per decade. That means 1 decade increased by 20 dB. Another decade increase another 20 dB. And it is positive because it's going up, positive. Right? So that one is Gs equal to S. And how about the phase angle? This angle, we say that is 90 degrees. So it is fixed 90 degrees. So if Gs equal to S is 90 degrees. Fixed omega. That is Gs equal to S. Let's see next. Gs equal to 1 over S. It's actually the same, but now we have 1 over S, just now S. So if we have Gs equal to 1 over S, then J omega is 1 over J omega. If I take the magnitude will be 1 is 1 over omega. Okay, omega, j omega, magnitude is omega. So 1 over omega. In dB, sorry, if we want to take in decibel, dB is 20 log 1 over omega. 1 over omega is omega negative 1. Same. Okay, 1 over omega is omega negative 1. Why I put omega negative 1? Because in log, we know that when power, we can multiply with 20. So actually minus 20 log omega. Previously, we get 20 log omega. But when 1 over s, it is minus 20 log omega. It's minus. Okay. For the phase angle, is 1 is 0. It's like day 1 is 0 degrees minus omega is here 90 degrees. So it is minus 90 degrees. S 90 degrees, 1 over s minus 90 degrees. Okay, let plot magnitude and the phase. Omega is magnitude in dB. Again, the focus point is 1. For log 1 will give 0. So it's 0 here. It's actually the same, 0.1, 10. You will get a line 20 dB per decade, but now negative. Negative 20 dB per decade. So it will be here, minus 20, then minus 40, 20, 40. So it will be a line like this, which is called minus 20 dB per decade slope. So the slope reduced by 20 dB when it moved to 1 decade, within 1 decade. It's shown here also. Say 1, 0 dB, then the other is going down, negative. Similarly, we can draw also for the phase is minus 90 degree. If this is 0 degree, it is minus 90 degrees. That is for 1 over s. It's shown also on the this graph. This graph here I extracted from the book, from the textbook. I just shown it here how we can get that one. Okay, let's move to this. What happens if we have 1 over s? S to the power of n. For example, s to power 1 over s squared. If we have, let's say, s to the power of n, j omega, we substitute s with j omega, so j omega n. If we want to take the magnitude, is actually just omega to the power of n. And in dB, 20 log omega to the power of n equal to n multiplied with 20 log omega. Okay, just now n equal to 1. Here what we did here is n equal to 1. So become 20 log omega. If 2, then 40 log omega. If s to power of 2, then 20 log omega. Similarly, the phase angle is it is 90 and that multiply with 90 degrees. This is the phase angle. Because 1 omega 90, the other one, if you have 2, then multiply with 90. Let's take this as an example. GS, if GS equal to 1 over S squared, it's actually equal to S minus 2. That means here N minus 2, the magnitude in dB is minus, we must solve this, minus 40 log omega. And phase angle is minus 180 degrees. We can plot for this. Still one, our interest 1, 10, 100 omega radian per second. This is magnitude in dB. Log omega, now 40 log omega. Still, when omega equal to 1, we get 0 dB here. But this is a line of, when we have this, it's a line of a straight line with slope or with slope minus 40 dB per decade. That means it increased, reduced by 40 dB. And then here maybe 80 dB is 0.01 here. 10 become another 40 dB, another decade, another 40 dB. So it's like this. It is a line slope with slope for minus 40 dB per decade. You will see that when 1 over S, all minus, because S at the bottom, S become the denominator, then become net minus. If S to power of 2, we multiply with 2, become 40 log omega. If S to power of 3, we multiply with 3, become 3 times 20, 60, minus 60 log omega. Okay, so if we have log omega, minus 40 log omega, that means it's a line, straight line, with a slope, minus 40 dB per decade. And the phase, if this is phase, will be minus 180 degrees. Okay, fixed. Constant minus 180 degree fixed value. That is an example of 1 to power of S squared over S squared. We have to know this in order to draw or to sketch or to use straight line approximation. Okay, let's move to a more complicated one. This is normal one. S over A plus 1. You can see that they are written in this form. Usually we have S plus A, but in Bode plot we normally write in this form. Later I will show you why we need this. So in Bode plot, normally written in this form. Okay, S over A plus 1. So we want this 1. Okay, what happens if we have S over A plus 1? Let's transform into the frequency response. Substitute S with J omega. So we get J omega over 1 over A plus 1. And the magnitude is here, is J omega plus 1. J omega over 1 is the magnitude. So we can imagine like this. 1 here, J omega over 1, this point. Okay. The magnitude here is square root omega over A squared plus 1. We can use Pythagoras to obtain the length here, or the magnitude. We want in dB, 20 log of this. Okay, so that for the magnitude. Then for the angle, for the phase angle, this is the angle that we want, theta here. Okay, so we can use tangent inverse omega over A over 1. So just omega over A. Right? Let's see, let's draw or sketch the Bode plot for this form. I will erase this first. Okay, let's see if we have to discuss 3 conditions. First, when omega equal to A. When omega equal to A, the magnitude in dB is 20 log square root. What A omega equal to A, that means A over A. So here 1 plus 1 is log 2. Log 2, if you check, is if you multiply with 20, you get 3.01 dB. That is for log 2. Is when omega equal to A. What happened? Second condition, if omega very small with respect to A. Very small. This the symbol here, small. I put 2, that means very small as compared to A. So the magnitude is 20 log this one. This term is very small because omega, when compared to A, very small. We can assume the first term in the square root becomes 0 because omega, when compared to A, very small. That means it's just log 1, log square root 1, which is 1, and log 1 we get 0 dB. What happened? The other condition, when omega very big as compared to A. That means (20 log Now, omega when compared to A, very, very big. So when we, that means A here can be ignored because very big, and 1 also here can be ignored. Because small, high value divided by small value is very big, we can also ignore 1, so become just square root omega square, which is omega, which is 20 log omega. And we know what 20 log omega is. 20 log omega, similar to the one with S, is a straight line with 20 dB per decade slope. That is for the magnitude. Let's see what happened for the phase. The phase here, also under the 3 conditions, when omega equal to A. So omega equal to A, tangent inverse 1. Tangent inverse 1 is 45 degrees. You take tangent 45 equal to 1. So when A, when omega equal to A, the phase angle equal to 45 degrees. For the second condition, when omega very, very small, okay, almost 0, we take tangent inverse 0, is 0 degrees. And finally, the last condition, when omega very big as compared to A, so it will be something like infinity, something like that. You will see it is 90 degrees, almost 90 degrees. Very tangent 90 degree, very big value. So this is how we use straight line approximation to approximate or to predict the Bode plot for S over A plus 1. So now let plot. Let's do the sketching. First, for the magnitude. Magnitude in dB. Here 0 dB. Okay, when omega equal to A, so A here is about 3 dB. So it's actually here 3 dB. Okay, but in straight line approximation, we will assume it's here. Is almost 3 dB. Is 3 dB near to 0. We just put 0 first. When omega less than 0, less than A, small, is so when omega small is 0 dB. What we do, below A, we say 0 dB. It is this one, 0 dB. After A, when omega very big as compared to A is 20 log omega. So what will we do? We get 10A, 1 decade, 100A, another decade. It will increase by 20. 20, 40. So this is the straight line approximation, which is 20 dB per decade. Line or slope. So when S over A plus S over A plus 1, this is the magnitude. Is from before A is 0, after A is 20 dB per decade. Let's see for the phase. Again, A, 10A, 0.18. That means 1 decade before and 1 decade after. We will see when omega equal to A, it is 45 degrees. 45 degrees is here. When omega small, it is 0 degree is here. Small, 0 degree. When omega big, it is 90 degrees. 90 degrees here. It's here 90 degrees. So what we do in a straight line approximation, we take A, and then we go 1 decade before A, which is 0.1, then we make it 0 until here. And we go 1 decade after A, we make it 90 degrees. Then we combine the line. This is a line with, you see, 1 decade, 45 degrees. 45 degrees per decade line. Positive. So when you get S over A plus 1, this is the root log, the Bode plot straight line approximation. Later, I send you just now before the class a semi-log graph. Later, we will do on the semi-log graph just to give you an experience. The graph will also be given in the exam with Bode plot, with already plotted. But we have to know how to read Bode plot. Right, so this is S over A plus 1. I took from the book, is the same here, S over A plus 1. Okay, now I replotted here. S over A GS S over A plus 1. Why I replotted here? Because we want to see a few important points from here. First A here. A is the place, is the point where from 0 it starts to go up here. Okay? A in this case is called break frequency. The point where it breaks from 0, then it go up. And here when angle 45 degrees, that is break frequency. Okay, so when you are given this transfer function, we straight away know this A is the break frequency. That's why in Bode plot we express in this form. We express the transfer function is S over A plus 1 form. Because we can get A, which is break frequency. It's very important. A is the break frequency. Okay, when we do here straight line approximation, we approximate below A and then after A. When omega very small, when omega very big. And that case, when omega small, we call low frequency asymptote. Asymptote means the line, the straight line. Okay, low frequency asymptote. Low frequency asymptote is this part. The part below A. And also this part for phase. That is low frequency asymptote. So when people say low frequency asymptote, that means below A, below the break frequency. We also have high frequency asymptote in which omega very big. That is here and here. A case after A. In controller design letter, you will be using low frequency and also, mainly low frequency asymptote. High frequency also will be mentioned. So when the term mentioned, you should know below A and after A. Okay, what we did just now is straight line approximation. The one here, the blue color, straight line approximation. Okay, this one. And this one. The straight line one. This is straight line approximation. This is for phase, this is for magnitude. And if you see here, this is the actual one. Plotted. We can use computer, we can use MATLAB to plot. This is the actual one. Okay, and this one also, the actual one. The pattern is there, is quite similar, but of course not exact. Just now remember when 1 radian per second, it should be minus 3 dB. Here minus 3 dB, minus 3. But in straight line approximation, we assume this is the break frequency, that it is the point that it changed from 0 to a straight line slope, with slope 20 dB per decade. Right, straight line approximation, but in the exam, if given, they will give you, question will use the actual one, the actual line, the actual Bode plot. Because it is, we plotted using a computer. Again, if people say straight line approximation in Bode plot, this is what we meant by that. We have just now 1 over S, we have just now S over A plus 1, but now we want to see the other one, 1 over S over A plus 1. It's actually the same. Only 1 over now become pole because it is in the denominator, and the result is almost similar, but it is now negative. It's negative 20 dB per decade. You can use the same technique. And finally, if you plot, it's here, omega, magnitude in dB. Our interest is A, 0.1A and 10A. A is the break frequency again, break frequency. So it will be, before A, it will be 0. 0 dB before A. After A, just now we plot going up, S plus A over S over A plus 1. But in this case, it will be negative. It will be going down here. Yeah, 1 decade will be minus 20 dB. So this is a line of minus 20 dB per decade. So 1 over. If you use the same, it's 1 over. That's why it become negative. Similarly, for the phase, our interest still A, 0.1A, and 10A. We have my minus 0 degree, minus 45 degrees, minus 90 degrees. Right? Before 1 decade before A, it is 0. When A equal to, when omega equal to A, it is minus 45 degrees. Because 1 over. Okay, negative, become negative. So here is 0. So it will be like this. And minus 90 degrees. This is a slope, a line with a slope minus 45 degrees per decade. So in order to draw, we have to remember the form, the pattern. And in order to remember, we need to do many exercises. You have to do many, you have to solve many questions in order to remember how to draw and how to remember the pattern. Okay. In the next class, this is the one I took from the book. In the next class, we will draw or sketch Bode plot given this system. Now become a big system. Remember, initially we just did one by one. One case, 1 over S, S over A plus 1, but now many. There are 3 poles, 1, 0, 1 constant. So what happened? How can we draw a Bode plot for this type of system? In the next class, next week, after Hari Raya, after holiday, we will do Bode plot. And we will use this one. I send you, I thought we can do it today, but we have to do it in the next class. Again, we will not ask this sort of question in the exam. You will be given directly this one with the plot. Okay, but I think if we do one at least, that will improve your understanding on Bode plot. Okay, any question? We will end at this point. At this time.
Sir,
Yeah.
so the test dates are fixed, right?
It is what day? I forgot actually.
18th May.
18 May.
Yes, sir.
No. It will change. It will be
is-
changed.
Okay, sir.
At
Thank
least
you.
1 week after. We will inform again.
Okay, doctor.
I saw 20 something.
Okay.
Okay.
Sir, will Bode plot come in the test, or are we focusing up to PID?
Part of Bode plot.
Okay, doctor.
Chapter topic 1, topic 2, and partly from topic 3.
Okay.
Okay.
Thank you, doctor.
Yeah. Any other question? How about the quiz last night?
It was okay, doctor.
Okay, Doctor.
Okay.
Okay. Not good, not bad. Okay.
The average is 2.7 over 5. All right. See you after holiday. Eid Mubarak
Doctor,
to
can
all
we,
Muslim
Doctor,
next week. But we're still in Ramadan.